Hi, welcome to the observability track at Scale 2025 in the observability track. Please join me in welcoming Dave McAllister, Senior Open Source Technologist with NGINX. And I believe this presentation is going to explain to us the statistics that help us interpret the alerts in our observability tools. Thank you, Dave.
Cool, thanks. Yes, I'm Dave McAllister. I work for NGINX. Some of y'all may have heard about NGINX. I think I've got maybe 2 or 3 slides in this because you can actually, there's a gentleman in the room, Tim Quinlan, who you can thank for actually causing me to write this talk 2.5 years ago. I used to do a talk on data science rules for observability, and every time I did that talk, there was one slide that always got questions. And Tim said, you should just build a chart that shows what you're talking about. And so I got carried away and I built the whole talk, figuring nobody would ever want to hear a talk on statistics. Okay, it has easily been the most popular talk I have ever given in my life. This will be the 47th time in the last 2 years. So if I skip things, my apologies. I am owned by 3 cats. I'm used to being ignored for that, so just keep that in mind. If you want to doze off, it's late in the day, feel free. There is no test in this. So before we get started, quick, what's the difference between a mean, a median, and a mode? How many people feel like they know what a mean is? And of course, nobody raises their hand. Median? Mode? Okay, so I know Tim raised his hand all 3 times. So what's the 9th data kind number? 9th data kind number was discovered in the middle of last year. It is the number of pathways in a monatomic logic circuit of 9 units. And I will give you the answer at the end, just because of this. I had to throw this slide with that extra credit question because I actually had somebody challenge me before I ever got through the first slide. So, monitoring is a numbers game. We are buried in data. There is so much data coming at us that we cannot keep up with here. The metrics are the numbers that represent what the system's behavior looks like. And it's usually time-stamped, it's usually key value paired, and it's useless unless it's aggregated, analyzed, and usually visualized. Nobody can sit there and look at a tail minus F of a log file coming in and have any clue as to what's actually going on. So when we look at that, and the chart that's over here is actually based off of open telemetry. It's a red rate error duration chart. It's sped up, and it's showing me a set of information that's coming in. I think it's aggregated into a 10-second burst based on 1-second feeds based on millisecond data coming in. And you can see quickly what's going on inside of that. So what are those numbers trying to tell us? Because those numbers have got to come out. That's the analysis part. So using my little bit, NGINX is an open source project. One of the most popular are web servers, reverse proxy servers, mail servers, load balancing, caching, you name it. It's kind of across the board here. And we look at things constantly when we're doing that to say, what's going on? What are the pieces of information? And to do that, we're actually going to be looking at the things, the open metric stacks or the plus pieces which add an API into this. There are lots of things that we can look in here. But again, what is the data actually telling us? Rule 1, the most essential metrics to track are the ones you need to track. And I can't make it any better than that because everybody needs to track something a little bit differently. But some questions you need to think about are, how do you deal with things like outliers? It's spikes. Spikes can go up or down. Keep that in mind for this. How do you get a representative value when things build upon each other? So you build a stack of results. How do you build those? And there are very specific ways of doing that. And how do you get a value of things that change over time? So how do you represent time in your equations? And this is where our alerts are trying to tell us things. We trust them blindly. Quick story. I did this talk. I was going to do this talk at a Google event. Google literally called me up and said, we want you to do the talk, but you've got to include AI. And I went, okay. So I went out with one of these things and I asked, I think it was Bard at the time, to give me the answer. And Bard came back with an answer, very clearly answer, and it didn't match mine. And I promptly assumed I was wrong. So I went out to ChatGPT and asked the exact same thing with the exact same data set and got a totally different answer. And I went through 5, and I got 5 different answers. Well, as much as I hate to admit it, Microsoft Excel has the function, so I went and plugged the data into Excel and came out with an answer that matched mine. And I felt a lot better about that at that point in time. But don't blindly trust the machines. They are not necessarily correct. Know what they're telling you is that. So let's talk about mean, median, and mode. This is a data set of 61 items. Almost all of these are a measure of central tendency that go into here. So a mean, measure of central tendency, and usually represents an average value for a set of data. The mean in this case, the one y'all are all thinking of, is 5.444. The median is the center item of the sorted list. Sort your list, count up and down. The one in the middle is what your median is. And the mode is the value that appears most often in the data set. And they all have different uses, and we'll go into that. But mean is 5.444. Or is it? Could be 4.130, 2791. Honestly, all 3 of those answers are correct, because I started off by asking you a trick question. I didn't tell you what kind of mean I was asking for. There are lots of means. Arithmetic is the one most of you think about, but there's a harmonic mean, a geometric mean, a trim median, a weighted mean, a moving mean, a double exponential of weighted moving average. Almost all of these cases have different uses, but the one we all think of is one in particular. We're not taking use of all those different pieces here. They also have drawbacks. They are all of these are already in your monitoring software. You just have to know to turn it on here. They give you very different results based on your data. And they make certain types of comparisons a lot easier. Like and unlike comparisons become a lot easier for that. So let's start with arithmetic. Arithmetic is the one you were all thinking of. Add all the things together, divide by the number of items, and it gives you a value. It's the central point in a normal distribution, that little bell-shaped curve, a Gaussian curve, normal distribution curve. It is not the 50% mark. This is something everybody always gets confusing. It is only the 50% mark if your mean is 0 and your standard deviation is 1. So in that case, it is. It's great for looking at comparison data, but by itself, it's not necessarily really useful here. And generally speaking, when we look at monitoring, we're doing this as time series basis. Either we're continually calculating a new arithmetic mean, or we're doing it as a moving target. You need to know which one it is. In a time series, your data can vary faster and more often than in a longer series. The longer your series is, the more stable your mean is likely going to be. There's less changes to show up inside of that. And so, standard load balancer, my load balancer puts out to its things, 100, 200, 300. Arithmetic mean is 200. Pretty straightforward. Doesn't really tell you a lot, but it's pretty straightforward. However, if that number suddenly jumped up to 3,000, it would tell you something. So the geometric mean is something we never did before computers came along, and even then it was not usually used over more than 3 or 4 items. Multiply the items together and take the nth root. And this is actually really useful when we're comparing things that are not alike. And so if you wanted to put a throughput metric with a volumetric metric, geometric mean is actually really useful for doing that. Geometric mean is most often used these days, not in monitoring software, but Wall Street uses it all the time when they're comparing companies particularly when they're looking at acquiring companies. And so as things grow, particularly as they grow exponentially, this is really important. So we can look at these things like average number of deploys per unit of time, MTTRs, throughputs all come into being. However, it also stacks. If you remember, one of those questions I asked early on was, how do you build things when they build on top of each other? And so if you want to know what your app deployment are in your DevOps team, you can actually look at the reduction of time for each of your sprints. Now, adding these together will come close. The more sprints or the bigger the number of differences, the less likely they are to match up. The geometric mean comes down here, and of course I'm subtracting this, so I'm showing what their functionality is. Build a geometric mean, and the geo mean is 9.37, and the arithmetic mean is 10.22. So some interesting differences here, but this is actually an honest viewpoint of how things are built and how each piece has improved on the preceding piece, bringing the preceding piece in. Harmonic. Harmonic is take the reciprocal of all the numbers, add them together, divide that into the number of items. And it was known as harmonic because it actually matches musical scales really well. And that's the reason it got named harmonic, of all things. And it's really useful when we have lots of multiple systems working together, or where things are not regularly spaced. And so requests coming in are not necessarily regularly spaced. And so harmonic is very useful for that type of data. Using the same load balancer episode from the front, my harmonic mean comes into 150. If you remember back at the arithmetic, it's 200. Harmonic is 150. In all cases, arithmetic will always give you the largest result. So if you're looking at the high value, arithmetic will always give that to you. Harmonic will always give you the lowest value because it weights the lowest number the most. And then geometric is sort of in the middle. So DevOps performance within a range of functionality becomes really useful. If you're looking at things that are in terms of use cases of how much something is getting used, harmonic will give you a very honest answer into how things are performing in terms of use categories. So let's talk about mean and how means can lie to you. And this is not a DevOps one, but it's fun. In 2023, the average income per person was $59,000 and change. The average household size is 2.63. Therefore, household income is obviously $156,179.92. Obvious, right? Wrong. The actual answer is $109,063. But it's obvious that the math works, but things will lie to you. If you use this mean structure for what's going on, and you want to make $1 million, you just need to have 14.8 kids. So keep in mind that the mean is trying to tell you what a central tendency is. And that's really all it's trying to tell you. And when we start looking at sort of a use case model, this was done in one of the talks. One of the people came up afterwards and said, when I'm doing consulting work and I'm looking at their, quote, observability numbers, I take the latency and I multiply it times the throughput, and that's the number that I use. The problem is that it doesn't weight either side. So if you look at this, my suggested metric for these first three is all 10,000, but my latency and my throughputs are drastically different in terms of what's going on. So this is the moral equivalent of a geometric mean. And it's very useful, but down here at the bottom, you can actually see what the arithmetic mean, the geometric mean, and the harmonic mean all look like for that same set of data. There's nothing wrong with making the decision, but what you've done by using this geomean model is you basically removed any weighting structure. And so you're no longer weighting whether latency is more important or throughput is more important. You're basically saying that they are equal. So kind of keep that in mind when you're looking at this. Now, the more observant people in the audience will note that there is a problem. I love these three means. I love talking about them. I think they're really useful. But there's a problem. Arithmetic means handle 0 just fine. Geometric means multiply all the numbers together. If you multiply times 0, everything is going to be 0, and taking the 100th root of 0 is pretty much meaningless. Likewise, harmonics is a reciprocal. 0 divided into 1 is undefined, and therefore anything that's using a 0 value, you cannot use one of those two means. In things like request timing or request arrival and throughputs, they work just fine. You very seldom have 0 as a request time or 0 as a throughput time. So, in Nginx terms, it's active connections. In web server terms, this is active connections that are going on here. It helps you understand what the load structure on your system looks like. You can look at whether you need to scale your resources here, and the variables don't matter for that. But it can also show you whether your system is working the way you want to and whether your changes are affecting the system. So depending again on what variable you're looking at, you may want to use a different thing. If you're looking at request timing, I would suggest strongly using a harmonic. And if you're looking at basic throughput, I'd probably say use an arithmetic. So that's, by the way, that is in my humble opinion. So, okay, median. Remember, median's the central value in a sorted set. This is the whole set of information that caused all the grief, because in observability, we do a lot of alerting on things like historical anomalies or sudden changes. And most of the times, people tend to use the mean as that value. There's a problem with that. Means react to the latest set of data inordinately effectively. And as you can see, for instance, two charts. I think the red is the median and the blue is the mean. I can't read my own notes down the bottom. But you can see over time, things sort of flatten out, things sort of stabilize. Now imagine that you've got a mean of 25, 25, the median at 26. So your normal behavior is around 25, 26 for this, and you suddenly get a spike. And that spike comes in, and now all of a sudden, you have an outlier spike of 250. Your mean reacts. It goes way up. And even if your system returns to normal, in this case, going back to these 25, 26 numbers, the mean slowly trails down, which if this is an outlier environment caused by a bug, caused by marketing deciding to offer a special sale and not telling you about it, your mean is going to trail back down, and you're going to have false data representation all the way through the rest of those things. Until you go back down to that normal status, your mean is no longer representing the status of your system. The median, in that case, moved one number. There was actually, it went up to 26.5 on this particular data set, but it literally moves one number. And so the mean can ride through an outlier spiking as a comparison metric better than the mean will. And until I drew this graph, I would draw pretty pictures in the air with my hands, and it didn't work. So thank you, Tim, for suggesting me to draw this graph for this. In DevOps, response time monitoring, this is really important to use the mean. By the way, remember I told you that means are not necessarily a 50% mark? Medians are always a 50% mark. So basically by using a median, you're using a percentile model. And if you are, great. I'll thank you in a minute. This actually just maps the same thing, showing you the harmonic mean. And harmonics also ride through the data better than any of the others do. So harmonics can be used, again, as long as there's no zeros involved. It will always be lower but nonetheless, it will ride through an outlier scenario quite well. So if you're using a P95, a P90, a P99, you're already kind of doing this median things, great, congratulations. But don't use the mean for historical anomalies or for sudden changes. It will hurt you in the long run. Okay, a little sidetrack. I've been talking a little bit about these things and referencing this thing called the variability. And the measure of variability is how the numbers behave. So you can do it with standard deviation. We usually do that one. But one of them that's really interested in and underutilized is this thing called an IQR, an interquartile range. And an IQR says take that sorted set, figure out what 25% is, 50% is, and 75% is. And those are your quarterly values. And the reason for doing this, we'll get to in just a second, but the reason for worrying about this thing is if I look at you and go, the mean, arithmetic mean is 67, or 61.7, it doesn't tell you a lot. It doesn't tell you that I've got 10,000 numbers. It doesn't tell you what the range is. And so, for instance, in Death Valley, mean temperature is 61 degrees. Feels really comfortable at 61 degrees here. The range is 15 to 104. So knowing what the range is equally important to knowing what the number or the metric is. And quite often in our monitoring, we only see the number. We don't actually see the range. And so what can happen down there is that, for instance, in two samples, I can have two sets of data with exactly the same mean and vastly different standard deviations. So my range is incredibly important anytime I'm talking about the mean. And if somebody just says, oh, the mean is blah, they're hiding something. So always make sure you get a range involved in that. Now, back to interquartile thing. The reason for it is this totally rule of thumb. There is no math specifically behind this, but it's quite often used. It's called an outlier formula. The outlier formula takes that interquartile value and says, what is this range between Q1 and Q3? Multiply that by 1.5, and then take that and add that to each end of the Q1 and Q3. And any numbers that fall outside of this can safely be considered an outlier. And this is something that, again, there's no mathematical basis for this, but it's something that statisticians use a lot because it's a great quick rule of thumb for those. Now, you'll probably see other pieces of data that fall inside of here. They may be considered outliers, but anything outside of this space is way out of range. So in the mode, most common set inside of here, usually histograph. We don't use it on our dashboards very often, but it's really important if you're looking at log analysis or user behavior. You see a lot of mode get used in security. Look at a log file and see how many failures. If failures are now coming in from a single source across all these different pieces, it's really important when you look at that. So mode is, in a sense, an indirect indicator of problems. But again, not often dashboard, except again in financial. You see a lot of financial things where people will go, oh, my mean is 97 cents, but my mode is $1. And so there's a different model that shows up for those pieces. Okay, sidetrack number 2. There are two types of statistics. There's this thing called descriptive. And descriptive is using the entire data set. There's also this thing called inferential. And inferential uses a sample set. So if I'm, for instance, talking about every single person in the world, I cannot use descriptive. I have to use a differential, an inferential model for this. Both get used for testing, both get used for trend analysis, both get used for visualization, but this leads us to a discussion on sampling. So monitoring is that data problem. One of my former customers I worked with at a former company did 43 terabytes of log files an hour. They added basically distributed tracing to this, and that number went up to about 91 terabytes per hour of data. No one can be descriptive with that much data. I don't care who you are. I don't care how smart your AI is. I don't care how many qubits you can put on your system. Nobody is handling that data for the next 100 years. It just ain't happening for that. So we usually end up sampling. And sampling can run a range from purely random to purpose-based sampling. And in observability, for instance, when we talk about distributed tracing, we usually have head and tail-based sampling. Head-based sampling is totally random. Figure out before you ever see the trace which ones you're going to save. Tail-based sampling, which is not actually sampling, says look for a condition to be met and save the data at that point in time. Now, why do we even care about those various things? So these are two samples, two different feeds. Now, they're not exactly identical because they were done with two different time sets. This one is sampled. And if you notice, there's one tiny little blip that's showing an error down here. And the latency, I've got one thing that's out here in the 1 to 2 second range. Using the exact same model running a few seconds later, not sampling, you can see I've got errors all over the place. Not huge, but I've got errors in lots of different places here. And my latency range is 25 plus seconds. In, again, e-commerce, anything over 3.7 seconds is considered a lost sale. Those are Google-based numbers. So if you're looking at this one, you think you're fine. You're not losing any sales. You look at this one, you're losing sales. So know what your sample is trying to tell you and make sure that you're sampling. The reason that you can say that tail-based model may work is that tail-based would actually go through and look at this and say, oh, you have an error, let me make sure that that is recorded. Whereas purely head-based random doesn't know what the results are going to be. The problem is this tail-based is not actually sampling. And because it's picking the things, for instance, errors, you may think you have bigger problems than you actually have. So if all you're doing is recording the errors, you're going to think that your system is broken. So you need to do a balance between the two. You need some that are random as well as some that are purpose driven. So sampling changes the behavior from descriptive behavior to the inferential behavior. It can hide outlier behavior depending on the model that you choose for sampling. And my recommendation, something that nobody's quite totally implemented yet, is you save everything in a block for about 20 seconds, because we know from looking at studies that if you have a code bug, 20 seconds of data recorded will usually indicate the bug. And then at that point, save a subset of random and a subset of tail-based, error-based. Someday, somewhere, somehow, I'll have enough time to actually write this thing out, but I don't have it at this point in time. Usually your metrics are not sampled. That's not true in tracing. Quite often you'll see it in tracing. It's a necessary evil. We've got to do something. We can't deal with all the data, but understand what it's telling you once again. Okay, sampling can also show bias. And people talk about survivorship bias, selection bias. Tail-based sampling can usually do that. It can also give you cognitive bias, which is where your interpretation may vary across there. The one that burns most people when we get into DevOps is this thing called recency bias. It hasn't broken recently, therefore everything is perfect. And my favorite XKCD on that one is, oh, you got married yesterday, so 4 weeks from now you better have another 28 cakes, because you're going to obviously get married every single day because you got married yesterday. So when there's that, you need to make sure that your recency is not complacency, and that you still consider the data and what it's trying to tell you at all different types. Distributions, we do a lot of curves. We look at lots of angles for these things. And the normal curve or Gaussian curve is the one that we think of. That's our bell curve. And our bell curve has this nice little thing, and it shifts around, and it can be all sorts of different shapes inside of here. Poisson curves are used to model sections of time across that. Betas, this is A/B testing. You have two things, you test one versus the other for that. Exponential, I'll talk about a little bit more. Weibull, likelihood of failure. You can actually use a distribution to show you the chances of something failing, which is really interesting. And then log normal is where you have a set of values that when you take the log of those values, they will map to a normal curve. It's kind of cool. And so things like throughput actually map really well to a log normal curve. Over here, you're actually looking at an exponential curve. This is actually request times, request rates that are coming in for that. So now, back to deviation real briefly. Let's talk about standard deviation, because standard deviation plays the most of a role with a normal distribution. And a standard deviation, everything figures it out, but it will give you the percentage of things, and so you can again look at and define what your outliers are going to be. Anything in this space, 68% of your values should come into one standard deviation plus or minus, and on out. It is not a percentage. Even though I've represented the percentages in here, I'm actually representing the chances, the percentage of values that are within there. Standard deviation itself is not percentage based unless you do this, take the mean and divide it by the standard deviation and then multiply by 100. And then you do actually get a percentage value from that. It's really useful when you're doing this to get through to upper management. Upper management seems to understand percentages better than anything else ever found. And so a standard deviation curve and showing them how things are lying in the outlying sections as a percentage seems to work better than almost anything I've seen. So Weibull, I talked about Weibull. And Weibull is something that was built more from the hardware side than anything else. And the hardware side says, take all the different little component pieces, know what the failure rates are, and then Weibull will show you what the chances of a failure are in a particular given time frame. Don't ask the math. The math is really ugly. Rust does this for you. R does it for you. Python has a library, and you just hand it the data, magically numbers come back. I've actually done this one more or less by hand just so that I can make sure that I was agreeing with the numbers, what was coming back from R from that. And so Weibull is usually used for time to failure. It's hard to use this with software, but it's actually really useful when you're looking at it from a hardware basis because they do test a failure and the data is almost always available. And then, so one of the things that I'm going to lead into is response time metrics. Response time is basically saying how long does it take the server to respond or to handle a set of requests, both from where it comes in to the upstream models that are responding or starting to this. And that gets us into exponential. Now, exponential's equation can look really, really fuzzy. There's actually one variable. That's it. So this lambda thing is 1 over the mean. E is a constant. And the only variable is this little x, which is your tested model. So looking at this from a latency viewpoint, I want to know the probable density of what happens at 158 milliseconds for a data set of latency coming in. And it says, if I pick 158 milliseconds, I have a 0.21% chance that I will have a request arrive at that time. But I can also build it as cumulative and say, okay, what are the chances I will have seen a request by that time? And it's 47%. Now, remember me talking about medians? Well, exponentials give you medians right off the bat. And so you can actually put a median structure for your request times or your throughput times the same way that you do a median across all of those other pieces. So, my pet peeve. This was written in a book that was given away for free. On scale, statistics are not your friend, which is wrong. On scale, probability is not your friend. Statistics are history. Probability is trying to predict the future. So statistics will tell me that my chances are 1 in something, and then my scale gives me the chances of something. So if I have a chance of failure at 1 in 1,000, and I have 10,000 things happening, then I have a chance of 10 things failing. But it has nothing to do with statistics. Statistics are just telling what has happened. And so, sorry, this one bugs the heck out of me, and so I've always included it in everything I do and I can't get them to change the stupid thing in the book. And they were giving away copies, and I was about to go through and scratch out that line every single place. They admit that they got it wrong, but they won't change it. So we're talking a little bit about this probability space. Coin flips 50-50, right? No, wrong. Tests have shown that a coin flip is about 51-49 for whatever faces up. Across 46 different currencies, they did 350,000 flips with live people for this, and 50.8 was starting side up. And it has to do with physics of precession, and just to make life worse, people learned to be able to flip the coin so whatever side they wanted to come up would come up every single time. So if you're doing a coin flip, ask the person to make the call before they ever see which side is up. Also, spinning is still random. So spinning is random, coin flips are less than random. So we talked about deterministic, we talked about definitive. Are you a determinist or a Bayesian? How many people are here at SRE DevOps space? Okay. Developers, okay. Developers are almost always determinist. DevOps and SREs are almost always Bayesians. I'm a Bayesian, by the way. So what the hell is this Bayesian thing? So Bayes theory is really simple, and it's best exemplified by this old game show, The Price is Right. In The Price is Right, at some point in time, you would get to stand with Monty Hall. It's called the Monty Hall problem for this particular reason. And in front of you would be 3 doors. Behind 2 of those doors are goats. Behind one of those doors is a car. You picked door number 1. Now, Monty knows what's going on. He knows what the car is. He knows where the goats are. And he says, I'm going to help you out. I'm going to open one of these doors. And he opens door number 2, and there's the face of a goat. And he says, do you want to change your pick or not? Okay, show of hands. How many people stay with the first door? How many people switch to the other door? Okay. Well, interesting enough, what Bayes' theorem says is that whenever you have new sets of information, you need to recalculate what you are trying to resolve. And it turns out that actually changing your pick is better. And the reason behind it, and this is, like I said, a really simple example, is that each door has a 1/3 probability of having a car behind it. You've locked in a door, so its probability doesn't change. The other 2 is 2/3 probability of wrong, 1/3 probability is right. He's now removed a door, so that 2/3 is now behind this door, that's where the car is. Now, Monty is also talking to you at the same point in time, and he demonstrated this to a reporter, did this 10 times with the reporter, and talked him out of the car every single time. He basically knew how to do this. But Bayesian theory says, whenever you have something new, you need to refigure what its impact is. So along the lines of, I think, I can't remember what the numbers are, but you've in a microservices environment, and you have just deployed a new microservice, and an hour later, something's broken. And you immediately start looking for the problem. And your first step is always to look at what's happened with that deployment. Okay, great. What happens if it's not the deployment? So by looking into this, you may suddenly find that it's not a deployment issue, it's a configuration issue. In a Kubernetes environment, you fail to set a memory limitation on some other process that's now sharing the node with your process, and it's starving for memory. And so by looking at these data, you redefine your steps. And so similarly, in any troubleshooting in a system environment, you constantly add new data to this, which puts you into the Bayesian camp. So honestly, Bayes says, honestly, if you've got 5% chance you'll crash on any given day, you start getting alerts about memory utilization, Bayes says you've got a crash coming. Okay, you know what your statistics say. You've got new data coming in. This is what Bayes says happens. Increase in error rates, 80% have been after major database insights. Bayes says, okay, it's probably a database. And all these different pieces come across, but this is the way that you can actually have saying, oh, it's not just my gut feeling, there's actually math behind this thing. And the math is actually interesting. And the side story on Bayes' theorems, Bayes came out with this theorem in 17-something, and everybody kind of ignored him. And it was picked up, another statistician in France rediscovered it independently and then discovered that Bayes had done this work. So that's why it's called Bayes' theorem for this. In the 50s, when they started looking at this more seriously, there were actual fistfights that broke out in the middle of the American Statistical Association's meetings, annual meetings, on whether or not Bayes' theory made sense or not. I mean, and literally fistfights, massive wars, publication, pro, con, people calling each other names. It's a fascinating history of something that even today we still have people arguing about. So Bayes is kind of interesting, but I am a Bayesian, I will admit that. Okay, so some common pitfalls to kind of finish up here. Ignoring scale, we talked about that one a little bit. This is at 61 degrees in Death Valley. Yeah, right, not necessarily at midnight for this. Looking at the wrong central measure. Are you looking at a mean versus a median? Correlation with causation. Anybody who was here for Upscale last night and got to see me play games with that one here. Failing to see your own biases. Survivorship bias is incredibly impactful there, where we just look at the data that we assume we can see here. And then confounding variables, which gets us into some of the correlation issues. So this is a correlation. Votes for Libertarian presidential candidate in California correlates at a 97%. 0.99 is perfection. This is Pearson's coefficient. Almost perfectly correlates with airbag recalls. The two have nothing to do with each other. There is no connection between these, but nonetheless, it definitely correlates. And when we talk about this, correlation is not causation. Correlation is ice cream sales go up in the summer. Causation is people get sunburned more in the summer. So both of them have what's called a confounding variable, and in this case, is temperature. A confounding variable for many of these things are hard to find or hard to recognize, but don't blindly assume that if B follows A, then A caused B. So along the lines of fun things here, Internet Explorer use directly correlates to murder rates. Anybody who was in the support category in the IE days totally understands how murder rates and the use of Internet Explorer correlate with that. And then my favorite sneaky correlation of all time is that marriage and beer sales are almost perfectly correlated. This is a 0.97% correlation rate as well, which of course leads to the question, does drinking cause marriage or does marriage cause drinking? The reason I can use this one both ways is that one of this represents a reverse correlation. So does beer sales cause marriage, or does marriage cause beer sales? One of them is forward, one of them is backwards. So in summary, statistics, how we analyze these metrics. We've got numbers thrown at us all over the place when we're looking at the alerting structure here. They're usually aggregated, they're usually reduced, and they show us central tendencies, so we have things to measure against here. They do not show individual behavior. Distributed tracing does show individual behavior on a behavior-by-behavior basis, but its aggregation shows us things like user happiness. Most choice make use of very few basics. We tend to stick with things like means, we tend to stick with things like normal distribution curves, but other things can give us some more interesting data that may show us other things. And then finally, the most effective tool is still careful thought, combined with judiciously placed print statements. And Brian Kernighan wrote this in Unix for Beginners in 1979. Metrics, traces, and logs are our new print statements, but it still requires us to be able to figure out what we're being told behind the scenes. And with that, this is the answer to the data kind 9 number. This is the number of pathways through 9 monological circuits. So there's a whole heck of a lot of paths that can happen inside of this. D10 is still not been discovered, so nobody's come up with D10 yet. And my famous quote, I have quotes sprinkled through here from various people: statistics are history. History is written by the winners. So keep in mind that your stats are showing what someone expects you to see, not necessarily what is. And with that, you can find me in lots of various places, and my slides are always available on GitHub as well. So, thank you. And then you've got time for dinner, drinks, and game night. Questions?
Go back to your Monty Hall slide, if you would. And when you said that you have new information comes in, okay, granted, okay, pick the middle door, it's not right, it's a go. But you left the probabilities at 1/3 and 2/3. Wouldn't this be 1/2 and 1/2?
No.
Why?
You have locked in the first one. The first one's probability doesn't change. You don't know what's behind that door, but its probability stays at 1/3. You now know that the other 2 doors together are 2/3 probability put together. Removing one door still leaves the odds at 2/3. I know it's, like I said, this was one of the most argued about things in the history of go back, come on. Oh yeah, everybody catches flack. Everybody catches flack on this one. But literally, yep. Yeah, so again, you have locked in 1/3. You now have 2 groupings. Think of it that way. You have this grouping and you have this grouping. Knowing that this is now a 0 doesn't change this grouping. Now, if he says, and I'm going to reshuffle behind the scenes and let you pick a new door, it's now 50-50. But because the grouping is still there. And this, like I said, the arguments are still going on about this. Now, mathematically, this has been run through multiple sets of simulations on computers. And the math actually works. It is better, it's about a 2/3 chance if you change, you will change to the right answer.
Yeah, let me suggest this. If you're assuming you're a programmer, you write a program that simulates this, and 2/3 of the time it's going to be behind doors 2 and 3 with a random distribution, right? But just pretend then that they came out that way, and you be Monty Hall and identify the goat on the other side, and
he would
ask
talk
yourself
you.
whether, what the outcome's likely
Yeah.
to be, and I think it sinks in then.
Yeah, and he would talk you out of it. When you were picking the door with Monty Hall, you had 0. That was your odds.
I work in data visualization, and one question that I have for you, since you're a man of statistics, I'm trying to explain to my boss that, having bar charts is better than having pie charts.
Sorry, say that last part again.
But
Pull the mic away.
having like bar charts and having more descriptive graphs is better than having pie charts that simplify things. Because you can have a pie chart where two percentages are the same, but
It's meaningless.
it's meaningless from one pie chart to another.
Right.
So how would you go about convincing a less, I would say, data-oriented person?
Yeah.
to
Believe it or
explain-
not, you just asked one. I should throw the slides in there because you just asked one of the questions I get asked all the time. And there's a second talk that I do that's called How to Lie with Statistics. And what I do, because I do use pie charts to lie a lot for those, and I sat down with execs and I lead them through the way the numbers are lying to them. And I then show them how I could take the same sets of numbers and show them meaningful data. That is the only successful way I have ever found of convincing them, is by showing them that I can lie to them. And again, I'm D.W. McAllister on GitHub. Grab a slide deck and have fun with it. That's one of my favorite talks. So, Tim?
So is there any value in analyzing your samples as aggregate pieces of data to say, all right, this sample itself was an outlier?
Yes, and that's actually what tail-based sampling tries to do, but it's not really sampling. Because if you are comparing a specific set of data to a set of criteria to which you have picked, then you are no longer sampling your data. So sampling by nature says that I am grabbing data and looking at what the results are. Statistically speaking, tail-based sampling is incredibly useful for DevOps environments, for monitoring environments, but is not statistically valid. It is not showing you the whole population. It's actually weighting the population to your criteria. It's survivorship bias is a tail-based sampling. I'm looking at things that manage to make it back to the base in spite of being shot full of holes, and ignoring all the pieces that crashed into the ocean because it got shot full of holes.
So is that like the once a measure becomes a goal sort of thing, like that it's meaningless?
It's incredibly meaningful, but it's not statistically representative of a population. So, cool. With that, I'm going to turn y'all loose, and I appreciate y'all staying with me and listening to me and laughing at the right places. I really appreciate it.
Well, thank you, Dave, and let's all